Welcome everyone to day 2 of this quantum school. Today, as I mentioned yesterday, we're going to talk about the Deutsche algorithm and about Grover's algorithm. In both cases, I will first give you a lot of theory, go pretty much into, so it's going to be math heavy. I hope no one is overwhelmed by that. And then after that, I will show you with Qiskit how to implement these circuits, algorithms. So I'll stop my video now to hopefully improve the Okay. So, as I mentioned, first we're going to talk about Deutsche algorithm. And what we start with is with oracles. So I will first introduce you to the concept of oracles. So for a lot of quantum algorithms, actually, we assume that we have access to some oracle, where this oracle can be just some kind of physical device. We can think of it as a black box, so we cannot look inside. But it somehow performs what we want, or some parts of what we want. And we can pass some queries to it. And then it returns some answers. So the goal then is that given such an oracle, we want to determine some property of this oracle. And ideally, what we try is we try to minimize the number of queries that we have to the oracle. So this maybe might sound like cheating. Okay, we have quantum algorithms and we just have some oracle that can perform any task we want. And with this, we can solve our quantum algorithms and some problems much faster than classical problems. And I agree, this sounds very weird. However, to give you an idea of what such an oracle, for example, could look like, I'd like to use the example of a phone book, which is not, okay, I will go more into that later. So as a phone book, you can think of the oracle as a phone book, where if I give you the name of someone, you can check what the phone number is. However, if I only know the phone number and I want to figure out what is the name that belongs to that phone number, since your phone book is sorted by names and not by numbers, it's really hard you cannot just quickly tell me which name this number belongs to. However, if I now ask the oracle, hey oracle, is this name the name that corresponds to this phone number? Then the oracle can quickly check and say yes or no. So this phone book example is an example that is used a lot to illustrate how oracles work. And I like it to give this illustration. However, one should note that the example of the phone book is something that is not feasible. Because if we wanted to create an oracle that acts like such a phone book, then we would need to first give this oracle all the numbers and connect it to all the names. So we would the oracle itself would first need to read in everything, the whole database, before it could actually help us with anything. And then, of course, this would be cheating, because then we cannot say we're much faster with our algorithm, because we would first need to create the oracle, which is too complicated to, this is not faster than just directly solving the problem without the oracle. But what one could instead use as a feasible oracle is if our oracle solves some satisfiability problem. So, or in general, if we have some constraints that we give to the oracle and we ask it, can this and this and this and this constraint be all satisfied at the same time? And then the oracle can say, it should be some constraints that the oracle can more or less easily check. And then it can tell us, yes, it's true, or no, it does not satisfy all at the same time. So an example, for example, would be Sudoku. We can then run some algorithms and give our oracle an input of different combinations of numbers and ask, ask it, okay, does it satisfy the fact that we have that we have each number exactly once in every row and in every column and in every box? And then the oracle, if it says yes, we know that we have a solution. If it says no, well, then it's the wrong solution. But so this would be an example that is actually feasible, more feasible than a phone book, but the phone book is just an illustrative way to explain what the oracle does. So let's see what on a classical computer. If we think of an oracle, I mean, it's just some function that has some input and some output. This function could have any input bit string 0, 1 to the power n. So that means an input string that has n bits. And then the output string could be any bit string 0, 1, so zeros or ones to the power m. So we could have any string as output that has m bits, where m could be different from n. However, on a quantum computer, we learned yesterday that everything has to be unitary and reversible. So also the oracle needs to be reversible. So if I have x as an input, the way I'm then constructing it is I have x, which has n qubits. Then I have my oracle, which I call OF, which implements the function f. And then what we learned yesterday is, in order to be reversible, first of all, we want to output x again. And then we want to output our function bits, our bits f of x. So if we now have m qubits as input, if we have n qubits as output, so if here on the bottom qubits, if these are m, then we also need to have m qubits, additional qubits as inputs, which we call the n-select qubits. And then as outputs, we can get y plus f. So in the easiest case, we just put in 0. So we put in x and zeros, and then we get out x and f of x. However, the input does not have to be x. It can also be some qubits y that can even be in superposition. So this is the way we would in general then construct the oracle if it goes from n to m qubits. Now what we call OF is a bit oracle. And it can be seen as a unitary or as a unitary gate. Which performs the map. If we apply OF to x and y. And then the output is x and y plus f of x. And just as a reminder, this plus with a circle around it means that we have addition modulo 2. So we add the 2 bits, and if it's 2, we take it modulo 2, so we take it to 0 again. Good. So in the algorithms that we will look at today and also the next days, we actually never consider more than one output bit. But so our function that we will always look at will be, the oracle function will always be from an arbitrary bit string on n bits to one single output bit. So the single output bit, for example, would be, okay, yes, this is the element that we were looking for, or no, this is not the element that we're looking for. And if we have such a function, then we can not only construct our bit oracle, but we can use the bit oracle and construct what we will call the phase oracle, UF. So we have, again, x as input. And then the second input, y, I told you we can choose it to be in any state. In this case, now we choose, because now y is only 1 qubit, and we choose it to be the minus state. So we learned yesterday, this is state 1 over square root 2, 0, -1. And we input those into our oracle. And then the output that we get is some y prime. And the other output is uf times x, and I will show you in a second why. Because actually what we can do is we will then call this box our oracle uf. So the reason we do that, why we just consider one input bit and one output bit and do not consider y and y prime, is because let's have a look at the action of the oracle on x and y. So what we can write, if we apply OF to x and y, we can write it as two parts. So we have OF applied to x and 0 minus OF applied to x and 1. This we can now just insert the y state. Now this we can write as x, because we just learned here about the oracle, the bit oracle. It gives us outputs x and y plus f of x. So it will give us x and 0 plus f of x minus x and 1 plus f of x. And now f of x can only be either 0 or 1, so we can look at the two cases separately. Let's start with first with if f of x is 0, then we get x and the first part 0 plus f of x. If f of x is 0, we just get 0. And then in the second term, we just get 1, which is exactly x and y. It was the case if f of x equals 0. And then in the case where f of x equals 1, we will get x. And then the first term, now we have 0 plus f of x, which equals 1. So we get 1 minus, and here we have 1 plus 1, which is 2. But 2 modulo 2 is 0 again. So we get 1 minus 0, which we can write as minus x times y. And now this is something that I found very confusing in the beginning. For me, having this minus now in front here, I thought that's weird. Why would I put the y to the very front? Now the reason is this whole thing, the way we do it with the wires, that is actually, it's not that the minus sign is on any of the two wires, but we always have to look at the total state. We cannot say, okay, we cannot really completely split the states of our different qubits. But in this case, we would have to say, okay, the minus 1, we have to look at the mathematical expression. And mathematically, if we write x times minus the state y, then this is the same as if we have minus x times y. And so this is also the same as if we have minus x times y. So this is all the same. I know it seems very confusing. Just believe me that this is true if quantum mechanics is true. So in this case, yeah, we can just get the minus out to the front. And then what we can write now is we can write it as minus 1 to the power f of x times x and y as a general form of our application of applying the oracle. What we see now, though, is this expression, minus 1. So if we look what the oracle acting on x and y gives us minus 1 to the power f of x times x and y. This is actually independent of y. So we put in y and we get out y. We don't really need y. So we do need it to construct it. So in the experiment, when we actually want to implement this function, we do need the y. However, if we just mathematically now want to say, okay, we're applying an oracle, we do not every time need to write down the y, but we just write down uf, and uf then includes this ancilla qubit. This qubit y here is our ancilla qubit. And if we write uf, then in theory, it always has this ancilla qubit. But for the future, we would just write x and then uf, and then the output is uf times x. So uf is what we call the phase oracle. Because before, our oracle OF gave us the bit, like it outputs f of x on the second qubit. However, now we will just get a phase instead. So the map it performs is UF applied to x will give us -1 to the power f of x times x. And now for x, we can also input some superposition, so then the phase actually is very important. Maybe I would now do already a small break for questions. Are there already questions? Oh yeah, there are.
Oh yeah, we've got tons of questions already. I was looking at the top one here, which is what is the difference between correlation and entanglement? That one seems to have a good 10 comments explaining the answer. So I think we can mark that one answered.
Okay, yeah.
That'll stay in the answered section, by the way. So for everyone that has that same question, when you click on the ask a question button at the bottom, there should be a little tab that says answered. You can click on that and see those answered questions already there. But the next one looks like here, is the Q-sphere unique? It seems different states can share the same Q-sphere plot.
Well, it's not, no, it's not exactly the same because, okay, I mean, it's on the topic of yesterday, but I can answer that as well, of course. So if we have the Q-sphere here and we have the states 1, 0, 0, I told you that they would be on these parallels. But now I honestly don't exactly know where exactly these states are, but we would have, for example, here we would have the state 1, 0, 0, and here we might have 0, 1, 0, and here we might have 0, 0, 1, which means that the first plot, where the first one that is mentioned here, which is 0, 1, as this one would actually then have this, have some blob here and another blob here, like this, while the other one, that is 0, 1, 0 plus 0, 0, 1, would have one blob here and the other blob here, of course in red colors each time. But yeah, I mean, it is basically the same if you rotate it, but well, we don't rotate it. The Q-sphere is defined in a specific way where like the state at the back is a different state from the state in the front. I hope this answers the question.
Cool, that's good for now. And let's, we'll keep moving with the lecture for now. And then if anyone has more questions about today's lecture, feel free to drop them in there. And remember to upvote to the top one. And I see some people saying, can we restrict them to today's lecture only? I hear you. So I'm saying help me out by upvoting the best questions for today. And then we'll get to those as soon as we can. So the power is yours. All right, thank you. Back to Elisa.
Okay. So the next thing that we need in order to then start with the Deutsche algorithm is we need to look at how the Hadamard gate, we learned about that yesterday, acts on n qubits. How we can write, there's a nice way to write down its action on n qubits. So let's recall from yesterday that if we apply the Hadamard gate to the state 0, we get the state plus, which is given by 1 over square root of 2, 0 plus 1. And if we apply the Hadamard gate to the state 1, we will get the state minus, which is also an equal superposition with a minus sign though. 0 minus 1. So if we restrict ourselves for x to be, the input bit x to be either 0 or 1, what we can write is, if we have x and then we apply the Hadamard gate, and then we get an output y, and this output y can be written as 1 over square root of 2. In general, 0 plus minus 1 to the power x times 1. Okay, so this would be, in the case of 0, we get just 0 plus 1. In the case of 1, we get 0 minus 1. Now we can rewrite that again, which might seem stupid now, but you will see why we're doing that. To 1 over square root of 2 minus 1 to the power 0 times x times 0. plus minus 1 to the power 1 times x times 1. That's just the same as before. I'm just adding this weird 0 times x plus 1 times x. The reason I'm doing that is because I want to write it as a sum so that it's clear. So I sum over k, all k in 0 and 1, minus 1 to the power k times x times the state k. So this is just a weird way to rewrite the action of the Hadamard gate on the state 0 and 1. But the reason I'm doing this is because now I want to generalize it for n qubits. So for the n basis states, so for all states 0, 1, the power n, so for all the bit strings that we have. So if we have our input x again, which is in this case now x0, x1, and so on till xn minus 1. And then we apply a Hadamard gate on all of them. And we get our outputs y0, y1, and yn minus 1, which is in total a bit string y. So which is h, we write it like this because you learn if we have multiple states, we put a tensor product between them. And if I now look on it, if I apply one Hadamard gate on each different qubit, then I write it h to the tensor product power n applied to x. And now what I claim, what we can write in this case, which is a generalization of the form we had before. And one could show, for example, with induction that this holds. So now I hope you can believe me that it's true, given what you saw before. You can write it as sum over, first of all, now we have a different normalization factor because we don't have two different states, but we actually have a superposition of all 2 to the n bit strings. So we need to write 1 over square root of 2 to the n. Then we sum over all these 2 to the n bit strings, which is this k in 0, 1 to the power n, minus 1 to the power k times x, and then, and then all states k. And here k times x, and that's what I have in the power, is the inner product of k and x. So if I have 0, 0 and 1, 0, it would be just 0 in the end. But I will show you actually in an example. So the reason we can see that this maybe also makes sense is because we know that every yi now, all of the outputs, because every xi was either 0 or 1, so all yi's are either plus or minus. Which means that they're always in a superposition of 0 and 1, each outcome. So the total state y must be in a superposition of all possible 2 to the n bit strings. And maybe just to give you now an example of, so you understand how this formula is calculated, especially with the inner product. I think inner product here, this k times x might be a bit confusing. So for example, if I have this as input state, the state 0, 1. So I have one qubit is in the 0 state and the other one in the 1 state, and I apply the Hadamard gate to both of them. Then my state y is given, according to this formula, it's given by 1 over square root of, oops, 1 over square root of 2 to the power 2 times, and now I have 4 terms. I'm summing over all the possible bit strings. The first one is k equal to 0, 0. So I take 0, 0 here in a product with x was 0, 1, times k times 0, 0. Plus, then I have the second term, minus 1 to the power, let's say 0, 1 times 0, 1. And here we get k is now 0, 1. Then we have k equal to 1, 0. And we have k equal to 1, 1. And if we now simplify this, we can see, okay, this 1 over square root of 2 to the power 2 is just 1/2. Then here the inner product, this one gives us 0 because we have 0 times 0 plus 0 times 1. So we have -1 to the power 0, so just +1. In the second term, we actually get a minus sign, -0, 1. Then we get -1, 0, sorry, +1, 0, because we have 1 times 0 plus 0 times 1. And minus here we get, again, a -1, so -1, 1. And this is actually also what we would expect if we think about, if we just calculate it regularly, we would see that here the first one is the state plus and the second one is the state minus. And if we multiply states plus and minus, we get exactly this as well. So yeah, maybe I can quickly do another question before we start with the Deutsche algorithm, because then I'm going to do it all at once. Is there maybe one question?
Yeah, I think we have this top question here. How do you determine relative phases for a multipartite system with no component in the North Pole direction? Is that relevant to what we're talking about right now? I'm sorry if it's not.
No, that's also for yesterday's.
All right, so we're gonna skip that one for now, and we're gonna move on to one right down here. We have seen yesterday teleportation, but since we need to send measures from Alice to Bob, can we call the global process? Oh wait, no, I'm sorry. That one.
That's also for yesterday.
Yep, that was
okay.
also for yesterday. How about this one? Why does the oracle need to be reversible?
The oracle, because we learned yesterday that quantum mechanics is always unitary. So yes, it is related to unitarity. We learned that there's actually a postulate of quantum mechanics that every possible evolution that you can consider is always unitary. So if we have the oracle and we have the oracle, or if we look at the action of the oracle, it also must be unitary. And if it's unitary, it is immediately also reversible. That implies that, yes.
Great, okay, thank you. And just once again, everyone remember your upvoted questions are the ones that we see first. So please upvote the ones that are most relevant to today.
Okay, so let's go then to the Deutsche algorithm. So to my knowledge, the Deutsche algorithm is the first quantum algorithm that showed how the good advantage that we can have when we're using superposition and quantum computing. This is why it's so famous, even though it might not have a very practical application. Plus, it's also very easy to understand compared to more sophisticated algorithms. So in this case, we are given a function f, which takes as input n bits, an input or a bit string of n bits, and then it outputs either 0 or 1. And this function is realized by an oracle. But we are promised that the oracle is either constant constant means in this case that all inputs map to the same output. So either all inputs map to 0 and it just outputs 0 every single time, or they all map to 1 and it outputs 1 every time. But if the function is constant, it means that no matter what we input, we would always get the same output. So we know that the oracle is either constant or balanced. And balanced means that the number of inputs that map to 0 is exactly half of the inputs and the other half maps to 1. So we know either we get 0 with half of the input, for half of the inputs we get 0, and for half of the inputs we get 1, or we always get the same output. This is what we promised by the oracle. And now our goal is that to determine which case we have. So whether f it's constant or balanced. Now let's look at the classical solution first. If we want to figure out what the solution is, we would need to ask the oracle once, then we get one output, but then we have no idea whether it's constant or balanced. We can ask the oracle twice, and if we get two different outputs, we immediately know that it's balanced. That cannot be constant. However, we might also get twice the same output, in which case we don't know yet whether it's actually constant or balanced, because you might just be unlucky, or whatever it is, that it's actually balanced, but that we just get a couple of times still the same output. So we then would need to ask it again. And we might need to ask it then in total up to n half over 1, n over 2 plus 1 times. So if we get twice the output, we need to ask again. And so on. And then at most, actually, which always happens in the case where it's constant, we cannot know whether it's constant or not. If we just get half of the time, for half of the inputs, the same output, we could have been by accident, just that we chose those half inputs that map to the same output, even though it's a balanced function. So to make sure that we're actually right, we would need to ask n over 2 plus 1, where capital N is 2 to the power n. So n over 2 is 2 to the n minus 1 plus 1 curies, where n is now the number of input bits, and capital N is 2 to the n, and this is the number of realizable bit strings. So maybe to give you just a demonstrative example, if we think of a coin and I tell you this coin, you want to figure out whether the coin is fair. And I tell you, okay, in this case, because we have only to allow for the n input bits, I could say, okay, you only have 2 to the n different ways to throw the coin. The question is the coin fair? So either with half of the time you get the same output and get one output, and the other half of the ways you get the other output, or you would always just get one output. I mean, that's a very simplified version, but yeah, that's something that one could think of. But yeah, let's see what the quantum solution is. In the quantum case, we only need one Curie in either case. And to see how that works, I'm going to give you the Deutsche circuit. So we start, as always, with our qubits in the state 0. And here we have n qubits. Then we apply on each of them a Hadamard gate. So what I told you yesterday, almost always we start by applying Hadamard gates to all qubits in the beginning to get the superposition of all states. Then we apply our oracle function, UF. Then we have, again, Hadamard gates on all qubits. And in the end, we measure in the 0-1 basis. It doesn't say anything else. It's always a measurement in the 0-1 basis. And when we measure, we get some classical output bits, Y0, Y1, and so on to Yn minus 1, which I call altogether Y. And now the claim is that if the total outcome Y equals the 0-bit string, so the bit string that has just n 0, so every single outcome would be 0. Then we know that f is constant. For any other output, we know that f is balanced. And now I will go with you through the proof. Hope it doesn't get too mathematical now. So we're going to check how the states evolve during the quantum circuit. So we look at how the state after each step looks like. So let's start with here. Here we have our state psi 0. Now psi 0 is just the 0-bit string because all qubits are initially in state 0. We can also write that at 0 to the power n. Okay, that was easy. Now the next step. The next step is when we apply all the Hadamard gates. So then we get the state psi 1, which is Hadamard gates on all n qubits applied to a state psi 0. And now we look at what we just learned. We use the Hadamard gate, the expression for the Hadamard gate on n qubits. So what we had here, this one. So we have 1 over square root of 2 to the n. Then the sum over all possible bit strings on n qubits. Then we have minus 1 to the power x times psi 0. And here we have x. But so now what we know is that here the psi 0 is actually just the 0-bit string, right? That's what we just looked at. So the inner product will always be 0, which means that this factor will always be plus 1. So we can just write 1 over square root of 2 to the n, and then the equal superposition of all 2 to the n bit strings. Good. So we can go to the next step. In the next step, we apply our oracle, and we get the state psi 2. So psi 2 is our unitary f applied to the state psi 1. And now, as we know that this is all linear, we can write it as, we can get this term, we can put the unitary inside the sum. So just as we had it here at the end of psi 1, we write the sum over all bit strings, but then uf times x. And now uf applied on x. We learned that's a phase oracle, and it will give us minus 1 to the power f of x times x. Okay, and now we have the last gate, the last step, psi 3. Here, what we again applied n Hadamard gates to our state psi 2. So we have our normalization factor, then the sum over all states, minus 1 to the power f of x. We use again linearity to get the Hadamard gate in here. Like this. We can rewrite that as sum over all x Now the same term again, but now we rewrite the Hadamard gate. We replace it with another sum, just as we did it before. Sum over all possible bit strings, -1 to the power, and this time now we're summing called the index k over which we sum. Now we have to take k times x, and then our states are k and not x anymore. And now we can actually change the order of the sums. So we get the sum over the k's to the front. In the other terms, we have twice this 1 over square root of, oh, sorry. We actually should already remove this factor because we have twice 1 over square root of 2 to the n. So I can remove the square root. And so now I'm just changing the sums and rewrite it a bit because we have these two -1 factors, -1 to the power f of x and -1 to the power k times x, which we can combine to -1 to the power f of x plus k times x. And then times the stick k. And this I define this part here now to be just a variable ck. So in a shorter version, I can write it as sum over all k, ck times k. And the ck we have defined by that, but we will then use this again to calculate. So our final state, psi3, just before the measurement, is given by this formula. It's a sum over all possible states k with different prefactors ck. Now we do the measurement on all qubits, and the question is, what's our probability to measure the zero string? Because my claim was that if we measure the zero string, we had a constant function and otherwise a balanced function. So let's see what the probability actually is now. And now we remember from yesterday, the Born rule, the probability to get the outcome all zeros by the Born rule is given by the projection of our final state psi3 onto the zero state. I take the inner product and the absolute values and then squared. And now if I replace the psi3 with the formula that I just wrote before, I get the sum over all k, ck, and then the inner product of the 0-bit string and the bit string k. However, now what we also learned is that, I mean, all the different bit strings, they're all orthogonal to each other. So this inner product is actually only one if k equals the 0-bit string. And if k equals any other bit string, the inner product is 0 because then they're all orthogonal. So instead of summing over our k, we just need to take for k the 0-bit string. So we just get c, the coefficient c, for the bit string, and then absolute value squared. This would be the probability. And now we just need to look again at how we defined the c and determine this probability. This coefficient c for k equaling the 0 string, and then we're done. So we have for ck 1 over 2 to the power n times the sum over all x over all the 2 to the n bit strings. Now we have -1 to the power f of x plus k times x. However, k is the 0 string. So no matter what x is, if we multiply it with a 0-bit string, the inner product will always be 0, so we don't need to consider that. We'll just leave that away. So we just have -1 to the power f of x and then squared. And well, let's look at what this sum gives us. We basically have 3 different cases. We have the case where f of x is constantly 0. If f of x is constantly outputs the 0-bit string, then we will always have the 0-bit, then we will always get -1 to the power 0. So we just get 1 for each of the 2 to the n possible inputs. So we will get 2 plus 2 to the power n. If f of x is constantly 1, then each time we will get a minus sign. So we will get -2 to the power n. And if f of x is balanced, then we will get for half of the terms, we will get 0. So yeah, we will get 0, which means -1 to the power 0, so +1. For the other half, we will get, this term will be -1. So they will all cancel out and we will get exactly 0. So summarizing that, we can say, if we then multiply it with 1/2 to the n and square it, take the absolute value, then we get, for the case where f of x is balanced, is constant. So one of the 2 first cases, we get in both cases exactly 1. Well, in the case where f of x is balanced, we just get 0. Oh, well, this is exactly what I claimed, because we just determined the probability after I apply the whole circuit. I determined the probability to measure the 0-bit string. And I said, okay, if f of x is constant, then the probability to measure the 0-bit string equals 1. So I would definitely measure it. While if f of x is balanced, the probability to measure the 0-bit string is 0. So my claim, that's exactly the claim. And we can see that with 1 query of the oracle and a measurement on all the qubits, we will immediately get the answer to our question. Now, maybe to give you very quickly an intuitive way to understand Deutsche Algorithm as well, is if we look at the circuit for what happens in the case where f of x is constant. Well, we know that we then have the oracle uf, which applies -1 to the power x, to the power f of x. So in the case where f of x is just 0, our oracle will not do anything at all, because it will just apply the phase, it will multiply with +1. So we will not have any change at all, and the effect of the oracle, there will not be any effect of the oracle. So in that case, we can basically cancel out the oracle, and then we see we have 0, Hadamard gate. We know that 2 Hadamard gates also cancel each other out. Hadamard gate times Hadamard gate equals identity. So we have just 0, and then of course the final state will again be 0. So it's clear that we will measure the 0 string. In the case where it's constant but outputs 1, it's very similar, because we will always get the -1 phase, which means that our total state will just get a global phase of -1. But as we learned yesterday, the global phase does not have any impact at all, no physical meaning. So if we just multiply with our oracle function uf, if we just multiply everything with -1, and then it has no effect, and we again have just basically 2 Hadamard gates, we go to the plus states, then we go back to the 0 states, and then in the end we will also measure the 0 state. While if we have a balanced function, the oracle uf will have some effect, it will change our state somehow. So if we then apply the Hadamard gates again, we will end up in a different state. Yeah, that's just to give you some idea of intuitive understanding of how the Deutsche algorithm works. And I actually think now it would be a good time for a break, but before that, I will answer maybe 1 or 2 more questions.
Sure.
And then we can have a 10-minute break.
Top 3 questions here are all pretty similar in what they're asking. They're kind of asking, how do we do this in real life? So the first question is, how do we implement an oracle physically? the next question is, how do we come up with algorithms with oracles since we can't build oracles in reality? So could you just touch on that really quickly?
Yes, so we can build oracles in reality, just not, for example, the textbook one, sorry, the phone book one where I mentioned, oh, we could have a phone book as an oracle. That's something that we cannot build. But for example, we can build a function that just checks whether some constraints are satisfied or not, like the Sudoku example that I made, or just, there's also this nice example that where I'm organizing a party and I have some people that I want to invite, but then I cannot invite person A and person B together, but I can only invite person B and C at the same time, or none of them. And then you have like you can make different constraints. You can form them into a Boolean function, and then you can basically give your oracle the input of, okay, if A is coming, B is not coming, C is coming. Is that a possible solution or not? So you just need sub constraints that can be 0 or 1, and then every time you can put in all these, the oracle can then just check, yes, it satisfies the constraints, or no, it does not satisfy the constraints. So it is possible to implement it. We will actually also, when we now implement we will implement our oracle with Qiskit as well. You will see how we're doing it there. I mean, that's maybe a different thing from how one would physically do it. But yeah, of course it's a big question in general, how to create the oracles. Yes, it's not always, for a lot of things, applications, it's not clear how one would do it. But for example, these satisfiability problems, one can easily, or it's feasible to write them as oracles.